So welcome back. Today we want to talk about front end. As I mentioned, we're going to start talking about advanced topics in computer architecture. Uh, Quick reminder that if you feel like you need background, two options that you have. One is going back and watch the lectures that my undergrad class has, or other similar undergrad classes. This is also the book that we use for our undergrad class. I definitely recommend you to take a look at it. There's another one from the same authors called Quantitative Approach. That one is more of an advanced book. Quantitative approach. That's a more advanced book. Generally recommend you to read them if you want to. Some of the things that we're gonna say is directly relevant there. Some of it are not. They don't talk about security at all, so the security part is definitely not there, but the other parts are there. So take a look. All right. So today we want to start talking about front end. And if you remember, I told you that this course we're going to mainly focus on this particular marker architecture. The way I'm going to discuss the topic is I'm going to give you the general themes and like the different design options. But then we're going to basically talk specifically about boom core and decisions that they make. What you will realize, and you probably have already realized, is computer architecture, like any other design systems, is all about trade-offs. So there is no like one single answer or one single way of doing things. It's always about, oh, okay, I can do this, but I can also do that. The pros of doing this is this, the cons is that, the pros of the other is this, the cons are that. And essentially, at the end of the day, based on the application or based on various different design requirements, one of the one of the design points will be used. So you will see that, for example, you have different options. It doesn't necessarily mean one option is better than the other. When we are teaching, I'm gonna give you those trade-offs, most of them. But then when we were talking about boom cores, since this is a concrete design, you're gonna see, for example, they chose to do this and that. Okay. And then this is also a reminder that we're going to use the third generation. There are lots of good stuff here. Many of the things I'm going to say today is actually on their GitHub. So they have a very nice README that you can go through and see the documentations. All right, so let's talk about front end. So what is a front end in a processor design? You can kind of like very high, at a very high level, you can divide the design into a front end and a back end. The front end is where it's interfacing with the rest of the system. That's why it's called front end. You basically kind of fetch and decode instructions, and then the back end is where you actually execute the instructions. And of course, you're going to have memory, which is kind of like, not front end nor back end kind of thing. So the main thing in front end that is happening is fetch and decode. Essentially, you need to bring instructions from the memory. There's some caching involved. The big thing about front end is branch prediction, which we're going to talk about, and then decoding the instructions to kind of figure out what that instruction is. What is the main thing that we want to do in our front end is how can we make things faster? That's basically the one and only concern that we have whenever we're designing a high-end processor is how do we make things even faster? And that's the main thing that we're going to talk about today, basically. For now, we're not going to be concerned about security and all that. We just want to make things faster. And things that I've described today is talking about high-end devices. So we're not even care about power that much. We just want to be able to get as fast as possible a computer ever. Okay? So this is actually a simplified, pipeline design of the boom core. Okay. As you can see, there's like a bunch of different things that is happening. This is fetch and decode and rename and dispatch. This is essentially where the front end and back end divide. So we're going to go through this one by one, and you're going to explain what it is. The main thing that you can see here is this fairly complex structure here, which is the fetch unit. As you can see, fetch unit in version 3 of Boom is actually 4 cycles. And mainly what it does is trying to read the instruction, but mainly what it does is bunch of different structures for branch prediction. So that's what most of the time it is. Most of these 4 cycles is for branch prediction, which we're going to talk about later. Today we're not going to talk about branch prediction, but then at some point once we do the fetching, we're going to put this instruction that we fetch into some form of a buffer. Okay. So this is kind of like, think about it as kind of like, we're bringing things, we put it into the buffer, and this buffer is going to be consumed with from the rest of the system. Okay, so that's how we divide the fetch from the rest of the system. Then, of course, whatever we are fetching, we need to decode it. So there's a decode logic. There's this thing called reorder buffer, ROB, which some of you know, some of them you don't know about it. We're going to describe it later. And then we're going to have basically the interface to the backend, which is what we call dispatching and instructions. That's what we're going to talk about next time. And then in the backend, we're going to spend a lot of time on the backend as well. There's like issue queues and execution units and memory units and all that. So just can give you like a big picture of how different things happens in this fairly complex out of order processor. Conceptually, there are 10 different stages in Boom. There is fetch, there's decode, register rename, dispatch, issue, register read, execution, memory, write back, and commit. The simplified version, which is the one that we are showing you here, is trying to combine some of these. So fetch is still at a stage, but decode and rename are combined, and rename and dispatch are combined, issue and register read are combined, execution unit, memory, and write back. And commit is kind of happens in the background. That's why it's not really a stage. So you don't want to put it in that way. But that's what we're going to talk about today. So we're going to talk about fetch, decode, and rename. And that's the only 2 things that we need to be worried about on the front end side. Okay. All right. So what are the basic operations that we need to be worried about in fetch in the front end? So we need to fetch instructions. What does fetch means? That we need to go to the instruction memory and bring instructions. Whether we bring just one instruction or multiple instructions, and how do we bring instructions, that's the thing we're going to talk about today. But eventually we're going to put it into the fetch buffer, right? And the fetch buffer, as I said, is going to be the interface from the fetch unit to the rest of the system. Branch prediction obviously also happens at this stage, because branch prediction is going to tell you where you need to bring your next instruction, right? So assuming that there is no branches, you just go straight line, right? You go next memory line, next memory line. Well, unfortunately, most of the programs that we have, on average, 1 out of 5 instructions is a branch instruction. So branch prediction is a big thing in any modern processor. So you need to do also this branch prediction during the fetch. You cannot do branch prediction during the decode or execution, because that's too late. You want to know what is the next instruction I need to bring. So you don't want to stall the processor. We're talking about really, really high-end processors that you want to keep the pipeline going, right? So you need to somehow magically know exactly, even if you see a branch, what is the next instruction that you need to bring. Then the decode is essentially just figuring out the things that are brought. What are those instructions? In RISC-V language, we're going to use what we call macro ops, which is kind of similar to instructions, but smaller basic block. And then we need to do renaming. And renaming is this thing that is specific to out of order execution. Most of you probably know what is the rename, what is renaming, but we're going to talk a little bit about different options. So just to kind of get an idea, how many of you know what is renaming? Raise your hands. Okay, half of the class. Okay. All right. So this is a more detailed view of the front end. So front end essentially starts with what we call an instruction cache. So this part is coming from the main memory. So this is your RAM. So this is where your instructions are stored. But during the execution, RAM is slow. We need to bring things into the cache. So bring it into an instruction cache. I'm going to talk about this, like the numbers, a number of ways, and so on. And then we're going to actually put it into instruction fetch. Then, as I said, you're going to put it into the fetch buffer and then the decode. And these things here are all your branch predictor logic. So there's a target queue with branch target buffer, a branch prediction unit, a return address stack, and a whole bunch of things that we're going to talk about next time. Okay. All right, so let's talk about these things in more detail. I'm going to take a step back and actually like do a quick review of how do we actually run a program from high level to low level, and then start talking about how do we make this process fast. Okay. So most of the computers that we are dealing with these days is called store programs, which means that there is some form of sequential aspects, and there is some form of relationship between memory and CPU. So essentially, if you think about high level, you write a program in C or Python or any other high level language. Then what happens is that you use this process called compilation, which you translate this high-level program into an assembly program. How do you do that? You use this set of standards called instruction set architecture, or ISA, right? So for example, in that laptop that the gentleman is using, it's an Intel processor probably, or AMD, so it's used x86, right? So that's a standard ISA that AMD and Intel is using. But the one that we're going to talk about mostly in this class is RISC-V ISA. Then, for example, Apple now has its own kind of ISA, which is based on ARM. But generally, ISAs are different for different companies, might be different. But the big ones these days is the ARM ISA, it's the RISC-V ISA, and x86 ISA. These are the main three dominant. Once we have our assembly, then there is this process from. So assembly, probably most of you have seen sometime in your life that there is something like for example, let's say if I want to add three numbers in RISC-V language, the syntax is something like this, which are these two are our source registers. These are our operands, and this is our destination register. This is where we're going to store this number. In RISC-V, we use X for our registers. So we don't use R1, R2, we use X1, X2, and so on. So this means that essentially what I want to do here is that I want to add X1 and X2 and write the results to X3. So that's what it does, right? So this is basically the assembly language. Hardware obviously doesn't understand this. The only thing that hardware understands is a set of zeros and ones. So we need to kind of translate this instructions into machine code. So that process happens again in the binary from assembly to the machine. We create that. Now that we have a machine code, this is basically what we call so-called binary file, which is basically a sequence of zeros and ones. We put this into the memory of our system. Usually we put it in the RAM. And then what happens is that, as I said, this is the store program order, or in other words, one Neumann model. In one Neumann model, what we do is we have a register called program counter, which points to the program that we want to run. And basically what it does is it's going to go through this sequence of zeros and ones. And for now, you can assume that every line in the memory is just one instruction. In reality, it's a bunch of instructions together. But if it's only one instruction, basically what it does is that this program counter register is going to point to this instruction. You're going to bring that instruction to the CPU, and the CPU is going to execute that instruction. And then you're going to go to the next one and next one and next one. This process of bringing this instruction to the CPU that's what we call fetching, right? In low-end systems, and that's what we mainly cover in our introductory class. So, okay, let's bring one and let's execute this, and then let's bring another and let's execute it. We never care about, what happens between this latency? Is this latency even acceptable? Because if this is really fast and it can run things really quickly, but if we bring it every 10 cycles, then it doesn't matter how fast I can run it. If I don't provide enough instructions to the CPU, then it's not going to be fast enough. So we're going to talk about how do we actually make this interface really fast in this lecture, okay? So as I said, we are looking at RISC-V. RISC is family of reduced instruction sets. A competitor to this is CISC, which is the complex version. What's the difference between RISC and CISC is that RISC is fixed size, which means that all the instructions has the same size. Typically, this is 32 bits for the ones that we're looking at. So all the instructions has 32 bits. And reduce means that each instruction is doing basically one thing. So one is doing addition and the other doing multiplication and so on and so forth. For CISC, it's a little bit more complicated. Instructions can basically have 16, but then some of them has then another 16 becomes 32. Some of them even have 4 of these and becomes 64. And then since you kind of combine them together, there are multiple things happens at the same time. x86 is the most popular CISC architecture, but CISC generally is not very favorable because it's very complex. Decoder becomes very complex, fetching becomes very complex. So there is generally an interest to go moving and shifting toward RISC architectures. That's why ARM is very popular these days. That's why Apple is built on top of RISC and so on and so forth. And apparently it seems that RISC is actually taking over in terms of speed compared to CISC. And that's actually one of the key reasons that Intel is not doing very well, is because their architecture is becoming so complex that it can no longer compete with RISC architectures. So, and then RISC-V, what is 5? This is actually coming out of Berkeley. They started with RISC-1 and 2 and 3, eventually 5 kind of taken off. RISC-V in particular is interesting because it's an open source ISA, which means that you don't need to pay royalty in order to build your systems. Generally, if you want to, for example, use ARM or x86 architectures, if you want to, let's say, build a CPU based on that and you want to sell it, you have to buy the license from the ARM or x86, either AMD or Intel. You cannot just go and sell things based on their ISA. So there is similar to you use software and you need to buy the license. But RISC-V doesn't have that. You can just basically build processors on top of the RISC-V ISA and sell it without any royalty fee. Simple structure of a RISC-V ISA is that you have a command and you have operands. These operands could be registers, could be memory, could be what we call immediate or just generally numbers, or it could be a combination of this. This is a general table that we covered extensively in my undergrad class. These are various different instructions. There are different groups, or some of them are ALU operations, some of them are memory operations. So kind of in the left, you see their kind of keyword that we use for each instruction. This is the actual syntax for each instruction. As you can see, for example, it's the keyboard plus the source and destination and operands and so on. This is the mathematical equivalent of this instruction. So for example, the first one is called load upper immediate, means that it loads the upper half of the immediate into the register. The second one is jump and link. This one is branch and so on and so forth. This is what's really happening in terms of execution of that instruction. So if some form of a constant, you shift 12 bits to the left and you store it in the RD register. So there are a whole bunch of these things. Well, obviously, we're not going to cover it in this class. Again, this is where you probably have seen this in some form of an undergrad class. You may not be familiar with RISC-V syntax. You probably in your classes, you've seen MIPS or R, very, very similar to those. But if you want to get familiar with RISC-V, you can just generally look into this table. And then, as I said, you can watch the lectures when I describe this in my undergrad class. And then, as I told you, from assembly, we want to create a machine code. Again, there is a standard for it. It's not like, you do arbitrary things. There is you say, okay, LUI, here's how you can actually create the actual binary for it. This part is usually called the opcode. This part is destination register. This is what we call func3. This is the source register. This is source register number 2. And this is the immediate part. Generally, for RISC-V, there's a total of 6 different types of instructions. Any instruction that you see in RISC-V will map into one of these types. So all we really need to know is how each type is mapped into binary, into machine code. Again, you don't need to do that. These are the things that are done automatically by the compiler. So as a designer, you literally don't need to really know, for example, this instruction, where is the output and so on. But generally, it's good to know that how these things works, okay? All right, so now that we kind of know this specific simple background, question is, how do we design this, right? And then how do we design this interface? That's really what the job of a computer architect is. Any questions so far? All right. So this is what we call a microarchitecture. So the design of a microarchitecture is design of this internal of this CPU. Essentially, what microarchitecture is a specific implementation of the ISA. So for example, I take RISC-V ISA, I implement it this way, I call this is my microarchitecture. Okay, but one RISC-V might have many different microarchitectures. So what I do with my design, for example, what we do with Boon is an example of implementing RISC-V ISA. But as I said, these are just some design decisions that we make. Doesn't necessarily mean that every RISC-V ISA should be implemented this way. There could be a competitor or another company that does it differently, and they might get faster implementation. So Apple, for example, is technically implementing ARM ISA, but they have some, proprietary, techniques and all that makes it very fast. Versus others that doing ARM are not as good, right? So those are the secret sauce that each company kind of brings to the table, right? So what are the things that we are comparing to consider when we are doing the microarchitecture? Number one, as I said, is performance. Number 2 and 3 is power and area. In some very rare cases, is security. But as I said, mostly the things that we're going to talk about today is the performance. Okay. So how do we design the CPU? At very high level, CPU is essentially like two things. It's a data path and it's a controller. And then is, as I said, is interfacing with the main memory. Within the data path, we usually have, as I said before, a program counter. We typically have some form of registers. Then we have some form of instruction registers that kind of like follow along which instructions you should do. We have some form of an arithmetic logic operation unit, ALU, and then we kind of like we have a controller that you can think about is kind of orchestrating things, stuff like say which data goes where and what should we do next and things like that. And of course, we need to back and forth communicate with the memory, right? So this is like very high level view of any microarchitecture. Generally, you don't see anything but this, right? But as I said, the details of each unit and what should I do with each unit, that's what makes a microarchitecture, one microarchitecture different than the other. But generally, that's the main thing that we follow for any design. Okay. To make this a little bit more complicated, last time we talked about superscalar. So essentially, what the superscalar does is think about that I create multiple instances of this data path so that I can feed multiple instruction streams to it, right? So if I have 4 of these and somehow have 4 of these controller, or the controller can handle 4 things at a time, then I can run 4 instructions at a time, right? So I'm going to have a 4-way superscalar, 4-lane superscalar system. Okay, but I cannot generally replicate the memory multiple times because memory needs to stay consistent, and generally memory is a very expensive thing. So we cannot just easily just increase and replicate memory. Okay, but we can, for example, have more bandwidth, so we can add more ports to my memory. But again, ports are also a very expensive thing, so there is some limit to it. But most of our modern processors are like 4 or 8 lanes, so they can actually run 4 things at the same time. We don't really go more than that because that's usually not going to be very efficient. At the very simple, this is a 2-lane superscalar. So for example, I have some PC and instruction. This is pipeline registers. This is my register file. And as you can see, I'm basically adding more ports, more read ports and more write ports. This is what we cover extensively again in my undergrad course of like a simple 5-stage pipeline in order processor. And again, if you're not that much familiar with it, you can actually go back and take a look at it. All right, so what is the main problem with superscalar? The main problem with superscalar is making all these units and lanes always utilized is very hard because why? Because there's dependencies. If you remember last time I said that we have instruction number 1 and instruction number 2 and instruction number 3 and instruction number 4, right? So you want at any given time be able to, for example, feed 4 instructions if it's like a 4 superscalar. But for example, if instruction number 2 is somehow dependent on instruction number 1, that result of I1 impacts I2, then I cannot run them in parallel. This one needs to kind of wait for this to finish, right? And then if I do these things in order, then essentially everybody else needs to wait because this one is dependent on this one. So then basically this one needs to wait and this one needs to wait and so on and so forth. Even if we do out of order, sometimes this becomes an issue because I need to search a lot of instructions to find 4 that are independent from each other. And that's not necessarily not always the case, okay? So what we do instead, as I said, we go from just thinking about this sequence of instructions one after another, try to see if I can search a very, very wide window of possible instructions and pick the ones that we can choose and feed it into the engine, the execution engine, right? And this is generally what we call out of order execution. Essentially, the out of order execution means that I'm running the back end out of order. The front end is still in order. So when I'm fetching in order, okay? I'm fetching multiple, but I'm fetching in order. I'm gonna have some form of a queue, the ones that I show you, the fetch buffer. But then when I want to execute them, I don't necessarily need to execute them in the same order that I put them into the fetch buffer. I basically go through them and see which ones are independent from each other. I start execute them one, as much as possible. I want to keep all of my lines busy, so that I get the most performance, right? So that's what we're gonna do with out of order execution. Because we are doing things out of order, then there are a whole bunch of problems arises. The first problem that arises, bless you, is we need to somehow do renaming that I'm going to explain today. But then the other problems also happens. For example, we need to know what happens if we make a mistake. Since we now run things out of order, we need to somehow be able to recover, and we need to keep track of what we have, reorder and all that. So we need to order back things into the order of actual, the things that we fetch, and that's why we have this a retirement or reorder buffer that we're going to talk about later in the backend. Okay. So how do we actually improve the front ends? Any questions so far? Yeah.
If we're using a FIFO buffer, how are we able to do it out of order, the execution? Do we just take a certain amount of size for the buffer?
It's not going to be a FIFO buffer. Yeah, so it's going to be a dispatch unit that. So essentially, there's going to be, if it's a FIFO buffer, then there's a dispatch unit that's going to then distribute this into some form of a big table.
Okay.
Yeah. Any other questions? All right. So now that you understand, hopefully, the basics, let's actually think about how can we make my front end faster. So I'm asking you this question, so that I want to do fetch, and I know that there's going to be a very hungry kind of execution units that, let's say, do 4 or 8 at the same time. What should I do to make my front end faster? Yes.
Fetch more instructions.
Fetch more instructions, right? That's the most trivial and obvious thing. You bring more instructions, you make your buffers and all bigger, and that makes things faster, right? So that's one thing. Anything else? Yeah.
Maybe cache instructions.
Cache instructions, right? Because you don't want to, every time you want to fetch, you don't want to go and bring it from the main memory because main memory is slow. So maybe you can bring even more and cache it into your cache, right? So, and then if you somehow know how to kind of do, so in the background, you bring things from memory and put it in the cache, but what you are interfacing from the CPU side is the cache, and cache is really fast. So caching is another thing that we do. Anything else? Yeah.
You do branch prediction.
You do branch prediction. So if you have good branch predictors, you always know what is the next thing that you want to bring. So even you don't need to bring a lot of things. If you have this oracle that you know exactly what you should bring, then you're good to go. Anything else? Okay, so let's learn what we should do. All right, so we bring more instructions at the same time. We increase the performance of the cache. We increase what we call the fetch width. And And then another important thing is that it's not just important that we bring more instructions. We need to increase the useful instructions that we are bringing in. Okay. So if I bring lots of instructions but I don't use those instructions, then it's not going to be useful. It doesn't matter how much we bring. And then of course branch predictions. So we need to improve the branch prediction accuracy. We also need to make sure that we're doing it in the very efficient manner, because if my branch predictor takes 20 cycles to predict, then it defeats the purpose, right? So you need to not only be accurate, but you need to be very fast as well. Okay. All right, so let's talk about this. Let's first talk about the first problem, fetching more instruction at a time. We already discussed this. So for a scalar processor, as you can see, if I have, let's say, a 6-stage pipeline system like this, at any given time, you can see that there are, for example, 6 instructions overlapping, right? At best, though, the best I can do with a scalar pipeline is that at any given instructions, I can complete 1 instruction at a time, right? In other words, my instruction per cycle is 1. We call it IPC. Why 1? Because essentially at any given cycle, if I look at this output, at any given cycle, I'm finishing 1 instruction, right? So if this is infinitely long, then you're going to see that in order to execute n instructions, I need n cycles, right? There will be like an initial 6 cycles to fill this pipeline, but after that, it's going to be 1 cycle per instructions I'm going to do. So I'm going to get almost close to 1, right? So that's the best I can do. For superscalar, as I said, what we do is that we make these lines more thick. Right, so thicker lines, which means that now I can run multiple instructions. So instead of having 1 instruction at a time, I have n instruction at a time. And again, if I have d stage of the pipeline, now I have n times d instructions at any given point. And now my IPC at best can get to n, and that's what I want, right? But this means that I need to be able to fetch n instructions at the same time. So my fetch rate needs to be n. But as I said, n is ideal, is that everything I bring is going to be used. Unfortunately, in reality, not everything I bring going to be used. So my effective fetch rate is usually much, much less than n, and that's what we need to improve, okay? So why don't we get that? So why in reality n is not what we get? Can anyone suggest? Yes.
You have dependencies.
If you have dependencies, okay? But I'm just talking about fetch itself. So even before we have dependency. But dependency is a good thing. I mean, good point. But even before that, there are other problems. Yeah.
Memory access time.
Memory access time, okay. But then let's say again, we are caching, so there is no memory access time. Yeah.
Branch misprediction.
Branch misprediction. Branch generally branches, right? So not even misprediction. Just branches. If I bring n instructions, I'm assuming that what n instructions do I bring? I bring n consecutive instructions, right? So when I'm bringing n consecutive instructions, I'm assuming that there is no branch within that n instructions that I'm bringing, right? Because if there is, let's say, a branch in the second instruction, then anything that I bring after that is potentially useless if the branch is taken, right? If I'm jumping somewhere else in my memory, doesn't matter how much I bring. Everything I bring is basically useless because I need to fetch completely different things, okay? So that's one big problem. That branches within that n consecutive instruction is going to mess things up. What is the second problem that we're going to have? Anyone? There is this thing called alignment. So essentially think about this is that, if all the instructions in the one memory is next to each other, if I bring all n, that's great. But if my instructions start somewhere in between each line, then I'm not going to be able to bring n. I can only bring half of it or less than that. Let me actually show you how it works. Actually, we need to do a quick detour, but let's not do the detour and let's talk about that and then do the detour. Okay, so this is the alignment issue. So for example, I have my cache, okay, and I want to bring instructions from the cache to the CPU, okay? So the way it works is that, let's say each cache line has 4 instructions in it, okay, and then it has some tag. So ideally, if let's say I want to bring 4 instructions, and then my cache line is nicely 4. So the way it works is that if my PC starts here, then great, I can bring all these 4 instructions. But if my PC is here, then I'm gonna have this misalignment issue, which means that I need to bring this instruction and this instruction one time. The next time, if I want to bring 4 instructions, I need to issue another load and bring this. Because I read things from the memory by line, by cache line, okay? So I cannot bring like arbitrary things from arbitrary points of memory. I can put one address and I get data from that address. If I want to read more, I put another address, I get more data, right? So if my addresses are somehow misaligned, so for example, it ends with 0, 1, then essentially the 4 instructions that I want to read are these, but essentially what I'm really reading is 3 instructions one time and 1 instruction another, right? So this is how we're gonna have. So these are the problems that we have in reality, that depending on my addresses, I may not be able to read that all n instructions that I want. So let me actually go back and talk about memory first, and then go back here and talk about this again. All right. So yeah, so fetching instructions. I want n instructions, and I'm gonna have 2 problems. I'm gonna have branch prediction problems, and I'm gonna have misalignment problems. So what are the trade-offs? The trade-offs is that obviously if I can bring more, seems to be better, right? So that at least there is a better chance, even if I'm gonna waste some of it, but bringing more is good. But on the other hand, bringing more means more power. It means that I need bigger bandwidth. It means that I'm going to bring some junks to my system as well, right? So I need to somehow store it somewhere. So I need to waste some space for buffering it and all that. So this is the big trade-off between the instructions. So first of all, how do we actually bring things? We bring things, as I said, with a program counter. Basically, program counter keeps track of the program. As I said before, jumping affects PC essentially. Normally, we run things linearly in the memory. That's why, for example, if I have n instructions run after another, I can bring n instructions and I'm good to go. But if I have this and then there is a jump here, it usually jumps to somewhere else. So this n instructions that I'm going to have, these instructions are useful, but anything after this instruction are basically wasteful, right? I'm not going to use them because I'm going to reset this from here to here, okay? And why we have a misalignment issue? Because of this, that, for example, if this address is 0, 0, maybe this address is 1, 0, or maybe 1, 1, and this address is somewhere else. Maybe it's 1, 0, 1, 1. Which means that it doesn't necessarily need to start from 0, 0, or it doesn't need to be multiple of 4 or multiple of 8. It could be anywhere in the memory, right? So that's why you will have this misalignment issue. If I can allow the system to jump wherever it wants, then it could start at any arbitrary address in the memory, and then we're going to have this misalignment issue, okay? Another thing that I said is we want to have byte addressability. So usually what we do is bringing multiple instructions or multiple bytes at the same time. As I told you, RISC-V is usually 32 bits, which means that it's 4 bytes. Means that it's 4 lines of memory. Okay, but then if I want to bring more, and then I'll bring more than 4, right? So the 4 bytes would be basically just 1 instruction. If I want to bring 4 instructions, then I bring 16 bytes at the same time, and so on. Okay. So why bringing from memories is a big challenge in our system? It's because memory generally is a very slow thing. There's this phenomenon called memory wall, that essentially I can increase the speed of the CPU because the technology that we're going to use is based on reducing the size of the transistor and all. But what people have found is that the performance of the memory is not growing with the same speed. Why? because the technology that memory is using is not the same technology as transistors are using. And this means that this difference between the performance of the CPU and the performance of the memory is growing. And this is what we call memory wall. This is actually a very big challenge right now because we know how to build very, very fast processor and accelerators. So for example, in the context of machine learning, we know how to multiply matrices very fast. But unfortunately, we are limited by the amount of data that we can bring from the memory. And that part we cannot really scale because essentially technology of the memory is very, very behind than the technology of our CPU and our accelerator. And it doesn't matter how good your accelerator is, as long as you cannot bring things, then it doesn't matter, right? So basically, that's what happens with memory, that we need to somehow hide this latency of the memory. How do we do that? We do this by using this memory hierarchy, right? So we have what we call caches, and we have multiple layers of caches. That what it tries to do is that it gives you this fast access to the memory, right? So essentially, if I go back here, memories can unfortunately be either very large or it could be very, very fast. It cannot be both, okay? So to give you some idea, usually we have what we call flip-flops or registers. These are very, very large pieces of memory, but they are extremely fast, so you can access them within one cycle. You put these registers very close to your CPU. Actually, inside your CPU, you have these registers. But since they spend a lot of space, you cannot have, let's say, 1 megabyte register file because it's extremely power hungry and consumes a lot of space. For example, each bit for a register requires tens of transistors, okay? That's how we actually build a flip-flop. So we only have small registers. We only usually have 1 kilobit of registers in our modern systems. We have like 128 bit, so 128 or 256 register, each one 32-bit or each one 64-bit. But we don't have that many registers because it's very expensive. So what we do is that we create this hierarchy of memory that it gradually grows in size, but gets slower and slower. So from registers, we go to this technology called SRAM, static RAM, which essentially, in order to store things, it only needs 6 transistors. It's much slower than the registers, but it's significantly faster than your DRAM and your disk. So we typically use that on our caches. So our L1 and L2 cache is an SRAM, okay? Then we go to another technology called DRAM. DRAM only requires technically 1 or sometimes 2 transistors to store 1 bit. Since I have much less transistors, it's significantly slower than SRAM and obviously than registers, but it's very, very economical in terms of space and in terms of power consumption. So this is my main memory. So like, 8 gigabyte of RAM, 16 gigabyte of RAM. This is what we're talking about. We're talking about DRAM. And then we go one step further. We go with disk. There are multiple different technologies. There is flash technology. There is solid state technology. There is older kind of laser and physical memory technology and so on. Hard disk drives. They are significantly slower, but they are extremely compact. So you can have terabytes of data in the same space that you would have had with registers. Another great thing about this is that they're typically non-volatile. So you can actually store things there without spending any energy, right? So just store it there. You can turn off your computer and your data will be there, okay? So when we have this, then we basically create this memory hierarchy that I showed you before, that we're going to have the registers inside the CPU. Then I'm going to have level of cache. Modern systems have usually 3 or sometimes 4 level of cache. We usually have an instruction cache. It's the one that we use for fetching. But then we also have a data cache that is used for caching the data. This instruction cache is usually level 1 cache. We show it as L1. And it's using the SRAM technology most of the time, but it's very, very slow. Usually we are talking about tens of kilobytes, so like 32 kilobytes, 64 kilobytes, that's the amount that you have because you cannot afford to have more. Your L2 and L3 and sometimes L4 could be bigger. So L2 is usually in order of 256 kilobytes. Your L3 and so on is usually goes in order of megabytes. Okay. For L2 and L3, we don't distinguish between instruction and data because there is no sort of locality at level of L2 and L3. So you don't need to separate the space for instruction and separate space for data. Why do we do it for L1? Because the pattern that you see for instruction is very different than the pattern that you see for data. So you don't want to mix them up because if you mix them up, they're going to destroy each other because data, for example, the reusability may not be that much. For instructions, the patterns are very different. So you want to reserve some space for your instructions. You want to reserve some space for your data. For L2 and L3, you mix them up because no longer you have enough space that you can both they can live together. And then after that, you're going to have your main memory. This is your DRAM technology. And from there, you're going to have your disk. Okay. So now that we understand why we need an iCache design, and we're going to actually talk about cache design a lot in this course. And actually, this cache design, unfortunately, is a very big source of security attacks as well that you're going to see as well. All right. So going back to the front end. So where are we? We are trying to make our front end faster. So far, we have understood that we need an instruction cache because memory is very slow. So I don't want to continuously talk to DRAM because talking to DRAM takes a lot of cycles. So I need to break things and put it in my instruction cache. This is L1 instruction cache. As you can see, it's 32 kilobytes for this particular design. But as I said, this can change from one mark architecture to another mark architecture. Since it's a cache, it also has tags. It's a cache since it has like virtual address that I'm going to talk about later. It also have what we call a TLB. Okay. But once I have that, then I can bring lots of instructions. So as you can see, what it brings is 128 bits. So it basically brings multiple instructions. If each one instruction is 32, right? It brings 4 instructions at the same time, right? And then basically it's pump out 16 bytes per cycle as it's fetching things. All right, so that's fetching more instruction at the same time. So we are kind of fetching 4 instructions at the same time, but we have that problem that I told you. We have the misalignment problem and we have a branch prediction problem. Let's have a quick break and we're going to talk about those things. Let's. Okay. All right, so now we understand iCache. Let's actually talk about how do we improve iCache. How do we optimize the performance of the iCache? Any suggestions?
Useful instructions.
Useful instructions? How do you do useful instructions?
Well, just making sure you're catching them instead of not ones that you're.
Okay, how do you do that? Okay, well, good thinking. Yeah.
You can change like the cache associated with your
Uh-huh.
number of lanes or whatever it's called.
Yeah. So you increase the sensitivity, or you do decrease it, or you increase it? Increase it. Okay. All right.
Use a more sophisticated eviction policy.
You use more sophisticated eviction policy. Okay. Anything else? Generally cache. How do you optimize the performance of a cache? That's maybe like a more generic question. Yeah.
Kind of like they get like direct access, you can do some like sharing or whatnot, that might save a lot of time access to memory.
That's what the cache does. But now we want to say, what do we do? So I want to design a cache. Okay. I understand that I need to put something between CPU and memory to somehow store things because it's faster to access that comparing to go all the way to the memory, right? So that's what the cache does. Now the question is, how do I optimize? Is it like I just put, let's say, Okay, I tell you that I have 32 kilobytes of cache. How do you design it? That's the question. Like, what's the strategy that I need to go with? How many rows should I pick? How many columns should I pick? What should be the strategy that we do to replace things like that? That's the question. Anyone wants to answer? Yeah.
Smarter prefetching.
Smarter prefetching. So kind of like, similar to the lane of like figuring out what is the useful instructions that we want to use. Anything else? Yeah.
Block size.
Block size, bigger block size, probably. It's a good thing. Yeah. So these are all good things. So these are the things that we do for improving the I cache, right? So first of all, you can improve the cache performance itself. And these are classic things that we do for caches. We're going to talk a little bit about it, and hopefully you've learned a little bit about caches when you were taking an undergrad class. So generally, the bigger the cache, the better the performance, right? So very simple. If I can somehow compress the code, again, I'm going to have better performance because I store less things, so I can store more useful things. If I reduce the number of conflicts, then I don't kick each other, don't kick things out of my cache. So I can use more useful things in my cache. So there are a lot of things that I can do to just make our cache a better cache. So someone talks about like replacement policy. That's another thing that I can do. If I improve the performance of my cache, that's great. The second group of things is increasing the locality. What does locality means? Locality means that there's two types of locality that we use. It's a spatial locality and temporal locality. Temporal locality means that if I use something, it's very likely that I'm going to use it again, okay, and again and again, okay. In instruction cache, do you think we have lots of temporal locality? Yes or no, or maybe? Who thinks it's yes and why? Someone wants to say, yeah.
You have like a loop.
If you have a loop, you're gonna then constantly read things. Yeah, so you're gonna have that. But if you don't have a loop, then you're not gonna have that much as temporal locality. Then there's another class of localities called spatial localities. Spatial locality is basically when you say that if I read instruction 1, it's very likely that I'm going to read instruction 2 and read instruction 3 and read instruction 4. Okay. So between data cache and instruction cache, which one do you think has even the best spatial locality? Yeah.
Instruction cache.
In-
The program mostly consists of like small sequences.
Yeah, instructions cache. Instructions are almost consistently is like one after another unless there's a branch. But then even for branch, you just temporarily jump somewhere else and then you begin to kind of go one after another, right? So that's why you actually have a separate instruction cache and a data cache, because data cache, you may not have a very good spatial locality. Your spatial locality could be all over the place, could be one after another, it could be two after another, it could be like 10 after another, depending on how you actually jumps over the array. But in instruction cache, like one after another, that's how you actually run your instructions, okay? So actually, when I have this, then the idea is that if I make my line bigger, remember I told you the way that we're going to read things from the cache is that we put the address, we read a line, okay? So this line could be at least a byte, okay? So at very least, each line should be 1 byte because we want byte addressability. But we can do more than that. So we can bring multiple bytes. We can do 2 bytes, we can bring 3 bytes, and so on and so forth. So for example, usually since each instruction is 32 bits, at the very least, you want to bring at least 4 bytes. If I do less than 4 bytes, it means that even for reading one instruction, I need to read the memory multiple times, which is not a useful thing. But in reality, we actually go much more, right? So if you saw the boom core, you saw that it's actually 128 bits, right? So we bring 128 bits. This is what we call a cache line. We make the cache line bigger, right? But how big? Should we go crazy? Should we go small? What do you think is the trade-off here? What's a good thing about increasing the cache line?
Or likely we'll get the instruction that we need.
Yes, you bring more instructions, and hopefully if you can use all of them, then great, right? One read and then boom. What's the bad thing about making big cache sizes? Yeah.
You have a lot of compulsory misses at the beginning because a lot of stuff is just like empty.
Yes, you're gonna have like at the beginning, you're not gonna have it. Anything else? Yeah, yeah.
Good branchy code that you miss. the
Yes,
calculus.
branching.
I think the power and the size are the same.
Yeah, the power, right? Like, you may not have enough bandwidth. You need to like have much bigger ports. So there are all those problems that you're gonna also have. So, but generally, if I want to increase my spatial locality, I bring more, right? So if I know that I have good spatial locality, I bring more things because I know the more I bring, the more I'm going to use, right? And as I said, spatial locality is inherent in program instruction stream. So that's generally a good thing, right? Something that Jerry mentioned, we're gonna do prefetching, right? So if I know beforehand that what I'm going to do, for example, I have a branch predictor and predictor says that this branch is going to be taken, although I haven't brought it yet, I can go and prefetch it, right? Prefetching is this idea that we can predict the future and go and grab things from the memory. You actually can do it for data as well, and it's been very widely used. Once we design and discuss cache design, you're going to see that. But generally, prefetching for instruction is also very common. And then we can also have things like streaming buffers and next line prefetchers and so on and so forth. These are different prefetchers that we're going to have. Finally, I can also have design my code such that I increase the usefulness of my instructions. So how do I do that? If I reduce the number of branches, right, I immediately fix the issue of spatial locality, right? So I kind of, if I lay out my code such that, I reduce the branches, I write different algorithms that doesn't necessarily have the branches all the time, or somehow I provide some hints to my branch predictor that whether this branch is going to be taken or not taken, these things can help me with, increasing the usability of things that I bring to my cache, okay? There's another thing called trace cache that I'm going to talk about it later, but that's essentially also helping with useful instructions. Any questions about iCache performance optimization? Great. So now going back to this question of, okay, I need to increase the line size. I need to bring more instructions. How many should I bring? And we are already talked about that, right? So we need to bring, first of all, we don't need to bring more than n. What is n? N is the number of lanes that we have. If I bring more than n and I cannot use it, that's basically already kind of dead on arrival situation. I don't need that anymore, right? So ideally, if I can bring n and use n, that's the most optimum design that I can have. Reality, though, is that we're going to have branch prediction problems and misalignment problems that are going to reduce the effective fetch rate from n to lower than n. So either I need to bring more and then hopefully reach to n, or I need to do some other things. So what is this a problem? Let me repeat what I said before. So I have my iCache, okay? And here, as you can see, the cache line size is 4, which means that I have 4 instructions here. So what I do is that I put the address, as I said, PC is the deciding where the address should be. So I have a bunch of things that is used for the tag. Typically, I divide the address into offset and the set. So for example, 010 decides that this 010 needs to be picked. Okay, so this is the set that I need to pick. And this 01 is basically the bytes that I want to pick, or the instruction that I want to pick. So for example, in this case, you see that it ends with 01, means that my instruction basically starts here. And from here, I want to fetch 4 instructions. As you can see, unfortunately, in this particular case, I'm going to have the misalignment issue, which means that I'm going to read one time 3 useful instructions and one time only 1 useful instruction, because I want to read 4 instructions at this system. So this misalignment issue is a problem that I'm going to face, right? So if I want to compute the average fetch rate in this case, you can see that if I have 4 instructions and my address could be any arbitrary value, it could be 0, 0, 0, 1, 1, 0, or 1, 1. And let's say it's uniformly distributed, so it could be any random value. Then my effective fetch rate gonna be 1/4 of time I'm gonna use all four. When is that? When my instruction, when my PC address ends with 0, 0. That's the best case scenario, right? But it only happens 1/4 of the time because in other cases could be 0, 1, 1, 0, 1, 1. In 1/4 of time, I'm going to use 3 useful instructions. This is the example I'm showing you here. 1/4 of time, only 2 useful instruction, and 1/4 of time, only 1 instruction. So on average, in this system, it's on average, I'm really bringing 2.5 useful instructions. If my PC could be any arbitrary value, right? In reality, though, I don't want to do this. What I can do is two things. One is I don't allow my PC to be any arbitrary values. So there are like bit shifting and things like that and masking I can do to make sure that my address always start from 0, 0. So there's one thing that we can do there. But if my PC can be any value, really in this system that I'm bringing 4 and my cache line is 4, what I'm bringing really is 2.5 useful instruction per type, per access to the memory. Does that make sense? Does anybody has any question why this is 2.5?
Is this only referring to the number of instructions or specifically useful instructions? I think it's just instructions, right?
It's instructions, yeah. So for now, assuming everything I bring is useful,
Okay.
right? So, but I want to bring 4, right? So because my n is 4, so I want to. But as I said, I put one address, I can bring 4. In this particular case, for example, I already read this from the previous 4, so that's why now my useful instruction is only 3 because the first one is already used in the past. Yeah.
Can you theoretically have all the jumps be aligned by having like compiler optimizations?
Good question. You can, yes, you can. So here again, I still haven't bring the jump thing. So I'm just talking about your PC could be any number. But yeah, if you, for example, what you're suggesting is that if I make sure that my PCs is always starts at 0, 0, and then any jump is also some multiplication of this, then I'm not gonna ever have a misalignment issue, which is true. That's what you can do, yes. But also keep in mind that not having misalignment issues that you have to kind of somehow add dummy instructions in your instruction cache, right? So you need to kind of pad it some way. So that's also another problem you're gonna have. Yeah.
How do you know it's a 1/4 of a time?
So I just made an assumption. I just say that PC, the last 2 bits of PC could be either 0 or 1, and it's uniformly distributed. So essentially my PC, 1/4 of the time is 0, 0, 1/4 of the time is 0, 1, 1/4 of the time is 1, 0, 1/4 of the time is 1, 1. That's just the assumption because I'm assuming that my PC is linearly increasing, so that's the assumption. And in this particular 1/4 is because my cache line is 4. So if this was 8, then it would have been 1/4 times 8 and so on and so forth, right? Any other questions? Great. Okay, so if I increase the cache line size, so if I want to bring 4, but then I have my cache line size 8, then what would be the fetch rate? Actually, let's you guys do it. So my n is 4, my cache line is 8. What is my effective fetch rate in this case? Can you compute it yourself? And again, assume that it's uniform, so 0, 0, 0, 1, so on and so forth. You have a number? All right, let's do it together. So in 1/5 of the times, I'm gonna have all 4. So that's what I'm actually gaining out of this 8. Why fifth 8? Essentially, this graph is showing here. If my address starts here, or here, in all these 5 cases, I can use 4 useful instructions. I can read 4 useful instructions. Okay. I bring 8. I'm using 4, by the way. So that's one thing. But at least I'm using all 4. But then there are scenarios that I'm not going to use all 4. What are those scenarios? 1/8 of the time, when my PC starts here, I'm only using 3 of them. In 1/8 of the time, when my PC starts here, I'm only using 2 of them. And then in some very, very unlucky situations, when my PC just starts right before the cache line ends, I'm gonna just use one instruction, one useful instructions. So if I add these numbers together, I'm gonna have 3.25 instructions per cycle, right? And you can clearly see that we are jumping from 2.5 to 3.25 by increasing the cache size. But what I'm losing here is that I'm bringing 8 and I'm using 4, right? And then even then, my effective rate is 3.2. But again, if this is a high performance, who cares, right? You want to bring more. So that's why in many systems, that's what you do. So you have bigger cache lines, you bring more things, you use less of them, but at least it means that now you have, and now if I have a backend that can execute these things, I can effectively reach to 3.2 IPC, that's what I want, right? So, but I cannot go beyond this. So that's also another thing that you have to see. So, and then you can do that as an exercise. You can do 16 and 32 and so on, and you can see the numbers basically grows. At some points, should be getting very close to 8 to 4. Yeah.
Is there ever a performance penalty for like increasing the size of the network, like increasing the amount of data movement?
Good question. The question is there a performance penalty? The performance penalty would be that when I increase this, I essentially slightly increase the latency. At some point, at the beginning I don't, but at some point I will. So that would be the penalty. So essentially, I'm telling you that now, for example, it's like 1 cycle to access the cache. But if I need to bring a massive amount, then it's no longer 1 cycle, it's going to be 2 cycles. So there will be a trade-off at some point. Any questions from this board? Cool. So now to make things a little bit more complicated, now let's say that on top of the alignment issue, you also have branch. So you have an offset. You go to somewhere in the memory. You want to bring, let's say, 4 instructions. But if in those 4 instructions that you want to bring, one of them is a branch, then the other 2 that you're going to bring no longer, useful, right? So let's say, for example, your PC starts here. In the past, I told you that, you can bring all these 4. So your useful instruction is 4. But if your branch is the second instruction and this branch is taken, means that these 2 instructions I'm bringing no longer is going to be useful, because the next instruction after the branch is not going to be this instruction. It's going to be something else, somewhere else in the memory, right? So now combining the alignments with branch, then our phase trace even reduce even further, right? So let's actually compute the same thing that we did before. Let's say my n is 4. It's also a cache line is also 4. And let's say I have a branch every 5 instructions. As I said, this is typically a standard number. And let's say my branch is always taken, which means that if I see a branch, it's definitely going to be taken. And then now assume that branch could be happen at any point, right? So again, the uniform distribution. So what would be your effective fetch rate in that case? First of all, should be less than 2.5 or more than 2.5. That's obviously. Do we have the number? Probability and statistic course class at this point. All right, so save time. I'm gonna just we can do it together. So we're gonna kind of like do it slightly different. So instead of starting it from the beginning, we started from the end because it's easier that way. So let's say that we start at the end. So if the start of fetch group is the last instruction, and that instruction is not a branch or a branch, doesn't matter. In both cases, we're gonna have one useful instruction. So worst case scenario, the PC will be at this point, and this instruction itself is a branch. It's still a useful instruction that we are fetching. So 1/4 of the time we have one useful instruction. Okay, so this is the most straightforward case. So let's talk about the other less straightforward. So let's say that your PC starts right in the middle. There are two possibilities. Either the first instruction that you're fetching is a branch. In that case, you only have one useful instruction. Or the first instruction that you're fetching is not a branch. In that case, the second instruction, regardless of whether it's a branch or not, is a useful instruction. So in some cases, you're going to have one useful. In some cases, you're going to have two useful instructions. What's the probability? So 1/4 of the time you start here. And 20% of the time you only have one useful instruction. In 80% of the time you have two useful instructions. So this is what you get. Any questions how we get this? All right, and then you're gonna continue. So now your starting point could be here. So if the first instruction is branch, then basically you just have one useful instruction because the other two won't happen. Then there will be also if the first instruction is not a branch, but second instruction is, then you get this number. And then if all three, like at the first two is not a branch, then you're gonna get this number. So how do you calculate that? 1/4 times 20% of the time you get this. 80% of the time you either get this or this, and so on and so forth. And then again, the last part is the one that's the most complex. So 1/4 of the time, if the first instruction is a branch, the second instruction is a branch, the third instruction is a branch, or neither of the instructions is a branch, or the last instruction could be a branch, doesn't matter, right? So here's how we calculate this. You plug in the numbers, you add them together, and you're gonna get 2.048. Okay, so that would be essentially your effective fetch rate for a system that has arbitrary misalignment and 20% chance of having a branch. So you bring 4, in most cases, you're only using 2 of them, right? And you could kind of like also intuitively say 2, because essentially if your branch can happen every 5 or every 4, you're essentially like half of the time you're not using your instructions, kind of thing. So that's how we actually can go with 4. We can go with 2. Any questions about this calculation? And could be a good exam, a good question for your exam that we do 16 and ask you to do it for all the branches and all that. So
How did you look at us and think we could finish that in a minute?
All right. So how do we solve this problem? How do we increase our fetch rate back to 4? Anyone? Yeah.
You could do the branch predictor and then like access multiple cache lines.
You can use a branch predictor and kind of like preemptively or proactively access multiple, right? Yeah, that could be a good solution. Yeah.
You can reorder those instructions
Mm-hmm.
so that if you have branch predict, like if you take the branch, you can get closer.
Yes. So if you move the branch at least to a lower part, like higher, parts of the cache line, or like at the beginning or end, or not letting to have this misalignments, these things can help for sure. Mm-hmm. Any other suggestions? There's one other suggestions that I'm looking for. It's actually an interesting solution. All right, let me actually show you that. So first of all, compiler can fix many of these problems. So it can move things around. It can basically let things to start at the beginning of each block and then move the branches or reduce the number of branches or move the block such that, you know, the branches are not taken and so on and so forth. You can write the code that has less branches. There are a lot of these things that you can do. Obviously, you can always bring more things as well. So that's also a given. The second option is what we call a trace cache, okay? And that's actually, again, many of the high-end processors use trace cache. So what is the idea of trace cache? Let's say I have something like this, okay? So as you can see, for example, let's say I have a misalignment here. I have A and B here. And again, I have 4, blocks per cache. Then let's say B is a branch, and then it jumps to C, and C is here, and then the D is here, and then D is a branch, and then E is here, and F and G, and then H, I, and J. Okay, so let's say we have the very, very messy kind of sequence, right? You can actually measure the fetch rate here. It could be also a good question for your exam. But then what I can do is, what if I can actually see the trace? So let's say I have this magic oracle that what it does is that it sees that you do A, B, C, D, E, F, G, H, I, J. Okay? So this would be basically the observed trace. Then what I can do is that I can remember this. Okay? I can remember this trace and I can cache this trace. Okay? So next time that you want to do this, and hopefully if this is something that you're going to do multiple times, let's say this is within a loop, instead of you going to the instruction cache, you go to the trace cache. And trace cache is going to give you this. And it's perfect alignment, right? So it's like your 4 out of 4, right? So you do first 4 and another 4. You can even make this bigger and make this 8. You can do a lot of things. So you're actually never going to have misalignment issue. You're never going to have branch issues. Although these are branches, but you're bringing the right instruction, right? So they're not consecutive in the original instruction cache, but they are consecutive in your trace cache, okay? So this is actually the idea of, like, originally was introduced in 1996. It's called a trace cache, a low latency approach for high throughput instruction fetching. And since then, there's been a lot of works on trace caches, and as I said, some high-end processors actually use trace cache. Okay. So essentially, to kind of summarize, trace cache basically observe. This observant could be some form of an offline phase by the compiler, or could be during the execution time. So the first time you're not going to perform very well, but assuming that this code can be reused, then you're going to have a very good performance since then. So if this is some form of a loop or some form of a function that you call many, many times, then you're going to have that. So there are a bunch of questions that, like, okay, how do I decide I should use the instruction cache or a trace cache? How should I update my trace cache? What should be the design of my trace cache? How big is it? Should be bigger than my general instruction cache, should be smaller. There are lots of good questions. There are a lot of papers published for those questions. If you're interested, definitely go and read more about it on the original paper and the papers that came after it. But generally, to give you like a very quick answer to these questions is that updating is kind of happens in the background, the same way that we update the branch predictor. So essentially, we see the sequence, and then the pipeline is responsible for updating it. In order to decide, you can use some form of a confidence. So you basically can measure the fetch rate, the online fetch rate, and see whether I'm getting good fetch rate or not. If I'm not getting a good fetch rate from my regular cache, I switch to the trace cache. If I see very good performance on trace cache, I keep using trace cache until I see again that I'm not doing very well, and then I switch back. So I can constantly switch back and forth between the two. I can also have some form of a voting system. So I can have like sequence from the trace cache, sequence from instruction cache, and then decide what you want to do. So there are a lot of these tricks that you can do at the dynamic time to decide which one you want to use. Bottom line is that it means more resources, but again, you remember I told you that it's all about I have more, how do I have infinite amount of resources, how can I use it in order to make things faster? And that's how one of the examples of how I do it. Okay? Any questions? Yeah.
Earlier in the role of the compiler slide, I'm kind of confused on what it means by basic block starts at the beginning of cache blocks.
So like here, so for example, I say that the fetch group can start here, 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 or here. What I'm saying is that if I can always start here and make it almost impossible to start at this point, then my fetch rate is going to
Yeah,
increase.
so the basic block just means like the block we start at.
Yes. The basic block, because we have branches, beginning of each branch is called a basic block.
Got it.
All right. So that's this part. As you can see, we bring in like multiple bytes. And now you can actually see that we have a 32 kilobyte EGWAY instruction cache. Okay. And now you can learn a little bit more. So this is actually a little bit more detail about the front end in Boom Core. As you remember, I told you that Boom Core has 4 cycles. Okay. So this is cycle number 1, 2, 3, and 4. So what happens in the Boom during the fetch is that you get your PC. The PC goes into the instruction cache. It gives you the instruction and put it into the queue. At the same time, there is a whole bunch of other things that is happening. So for example, we go to the BTB, which is for the branch prediction. We go to branch predictor and a whole bunch of things. There is some form of an address computation going on that I'm going to describe later. But eventually, at the end of the day, we're going to have my address, and I'm going to put that address into my fetch buffer. These things are only just checking whether we have a branch or not, and should we update our branch predictor or not. Here, that's where we can also do our trace cache, basically. So our trace cache can also be implemented. The logic would be implemented somewhere here, and we can update our cache that way. So our trace cache, for example, will kind of sit here next to our instruction cache and provides instructions to the next level of the cache. Okay. Some specifics. So Boom particularly reads instructions aligned, so it doesn't support misalignment yet. Boom itself is a dynamic thing, so it's actually changing. So the way it works is that it fetch one group, it waits that group to be consumed, then it fetch another group. So that's how Boom works. It cannot read across cache lines, so it can only read one cache line at a time. Boom also does not support this thing called hit under miss, which hit under miss is this microarchitecture feature that if you have cache behavior, like for example, if the data that you're looking for is not in the cache, what you can do are 2 options. You can either stop everything and go and fix that issue. You handle that request, or you can continue servicing other requests while you're in the background, you fix that issue, you bring the data. This is called hit under miss. Boom doesn't have that. Again, for that, you require additional circuitry. For now, if there is nothing in the instruction cache, for example, you have to wait. You have to stall the processor. Okay? iCache is also what we call a virtually indexed, physically tagged cache. How many of you know what that is? I actually described that in my class. Okay, so some of you know. How many of you know what is a virtual address? Okay, a few. All right. So let me actually quickly also review that. So what is a virtual address? Virtual address is this notion that we have in our systems because we want to have. We don't want to be worried about actual physical addresses. So if I have a bunch of different programs in my computer, okay, each one thinks that they have access to everything in the memory. Okay, so they think that everything is for them. It's a large and unified memory. There is no segmentation. There's no fragmentation. You can divide each program into sections. So for example, you can have a reserve part, you can have a code memory region, data region, heap and stack that can grow in different directions. But if I have n different programs, all of them thinks that they have access to the entire memory. Okay, they don't know that they, for example, this region is for them and the other region is for someone else, because they don't have the mapping information of the actual hardware. In reality, though, of course, you have an actual physical memory, which is limited in size, is even smaller than one of these programs that thinks. So what do we do to kind of like handle this obvious conflict? We do this address translation. So we have a program, the program use addresses called virtual addresses because these are not real addresses. These virtual addresses needs to be translated into physical addresses. Once we have actual physical addresses, then we're going to access the memory. Okay, so memory only understands actual real physical addresses. Program has no idea what is those physical addresses. Okay, how do we fix that? We fix that by this notion of what we call page. Okay, so if this is my physical memory, what we do is that we fragment physical memory into smaller regions called page. Usually think about each page as 4 kilobytes. So a continuous 4 kilobytes region of memory is called one page. So for example, here, every color is one page, okay? So then what happens is that now that I have a program like program A, then I'm gonna fragment the virtual addresses into pages as well. And then I'm gonna map each page of my virtual to a page in my physical, okay? And then this address translation then gonna give me the real addresses into the memory. Interesting thing is that now this physical pages doesn't need to be continuous. So for example, this first page might be address here, the second page might be here, this third page might be here, and so on and so forth. So they could be scattered all over the memory. It doesn't matter. As long as I know where each page is, then I'm good to go. I can always go and look it up, right? Why would I do this? Because this gives me a lot of flexibility, because now I can introduce a new program and all I need to do is creating new set of pages and map them into a real physical pages. How come that we actually have this large program virtual, but only have small and still things fit? Anyone wants to answer this question? Yeah.
The vast majority of the time, the program doesn't need that much memory.
Yeah, so in vast majority of time, these virtual pages are not assigned yet. So remember that we only assign physical pages when we are actually using it. So although the program thinks that it has every pages in the world, in reality, we only assign pages that they actually use. If they need more, we're gonna assign more. At some point, we might run out of memory, and probably some of you have seen that you have run out of memory when you're running large applications. But in majority of the time, if your system is performant enough and you have big DRAM, then you're not gonna run out of memory, because regardless of how many programs you run, you always have enough space in your system. But if you run two massive programs, then you're gonna run out of memory and your system gonna crash. All right?
If
Yeah.
you reach that point, couldn't it also just do swapping as well?
It can do swapping, but then if you do swapping a lot, then you're gonna be frozen, and that's when you're gonna crash. Yeah, but yeah. Okay, so how do we do this translation? This translation happens in this thing called page table. Okay, so how does it work? We're gonna have a virtual address. Our virtual address could be n-bit. Okay, our physical address could be m-bit. N and M could be equal, could be not equal. For example, if my physical memory is smaller, then M could be smaller than N. But as I said, since not all the pages in my virtual is actually assigned, then it's no problem. What we do is that, remember that my addresses needs to be byte addressable, but I told you that my pages are 4 kilobytes, 2 kilobytes. That's why we have this thing called page offset. So the bit 0 to bit p minus 1 is reserved to address the bytes within one page. That's why we call it page offset. So if a page is, for example, 4 kilobytes, it means that I need 2 to the power of 12 bits to address each individual bytes within this 4 kilobytes. Okay. That's why this is basically 0 to 11. So bits 0 to 11 is just for addressing 1 byte within 1 page. The rest is basically the page number. Okay. So it's a virtual page number or VPN. You feed this virtual page number into the page table. Page table is basically this table that what it does is that it has a virtual page number and physical page number. This is a mapping, right? So it gives you the physical page number. The page offset basically comes here directly because this is an offset, it doesn't need translation. This is how you build your physical address. So the idea of address translation is that you take your VPN, you go and find the equivalent of your VPN in that page table. You bring that PPN, the page, physical page number. You add your offset to it, and now you have your physical address. And now you can go and actually access that wherever that is in your memory. Okay. Where do I store the page table? This table itself, where is this one stored? Since this is a massive table, because essentially for every page I need an entry, unfortunately I need to store this itself inside the memory. Okay, because remember, for every single process I have a separate page. Okay, so if I have like 10 different processes, I have 10 different pages. Each one has a bunch of pages that are mapped. So it's a massive amount of memory required for pages. So I cannot have like a dedicated memory for my page table. I usually use the memory itself. So what is the problem here? The problem here is that now accessing the page table itself requires translation, right? So it's kind of like a chicken egg problem that the page table of you need a page table of the page table and so on and so forth. And then the second problem is the massive performance hit that you're going to get from this, because now what used to be that I just wanted to go and bring something from, let's say, my cache. Now I need to first translate the address that I want to use from my cache. How do I translate it? I need to go to the memory and bring the page table, translate it, get the physical address, and then go to the cache. So there's like a huge performance hit in terms of like, how things are gonna get very, very slow. Okay. So how do we fix this? Use this thing called TLB, translation look aside buffer. So the idea of TLB is that I'm gonna remember the latest translation. The idea is that I'm gonna get a lot of spatial and temporal locality, because remember I told you pages are 2 kilobytes, 4 kilobytes. It means that if I go like line by line, byte by byte, there's going to be a lot of next byte, all fit into the same page. So if I remember the first translation of the page, I don't need to continuously go and look it up. I can just remember that this page is the VPN of this page is this. Okay. So all I need is to just add the offset to this, and every time that I want to access it, I just add the offset. So no translation necessary, right? Where do I store this? I store this into this structure called TLB. TLB is like an L1 cache, okay? So it's a small, it cannot be big, because if it's big, then again, it's gonna get slow. So it's very small, but it's very efficient because it can remember many, many things, okay? So here's going to be what we're going to do in our memory hierarchy. So in the past, remember I told you that I'm going to have my CPU and my registers. From the register then on, I need translation because everything is virtual at this point, right? So everything here is virtual, but everything here is physical. So I need translation happening here. Usually what we do is we have this memory management unit, or MMU. MMU, that's the simplest form. All it does is it has a TLB, okay? Either you see that translation in your TLB, then it's a hit, then great, you have your physical address, you don't need to do anything else. Or you don't have that translation in your TLB, you go to your page table and then you translate it and you come back. If in most cases I go this route, I'm not going to see any performance hit, any problem, because accessing TLB is very, very quick. It's accessing as fast as accessing L1. If in some cases I go here, I pay that penalty. But if like 95% of the time here, then the average is almost big, right? So that's what I do for accessing, okay? But if you look at the hit time, at best case, the hit time of accessing L1 or my I cache in this case is going to be the access time for this TLB, right? So the time, so my hit time, it means that the time that my instruction do exist in my instruction cache and my translation do exist in the TLB going to be the time I take for looking at TLB plus the time it takes for me to access things from the L1 cache, right? So this would be my hit time. Remember, without address translation, my hit time would have been TL1, right? So I'm kind of paying an extra penalty of TTLB here, okay? It's not too bad as long as my TLB is very small, but still, it's not great, okay? So how can I get rid of this? That's the idea of virtually indexed, physically tagged caches, okay? So by the way, this is how TLB looks like. So essentially your VPN is going to be stored in this kind of tag architecture. If it's there, then you don't need to go to the page table anymore. But now the idea is that I want to somehow also really get rid of this TLB. And I want my hit time to be equal to just hit time of my L1 because that's the minimum I can have, right? So I need to somehow access TLB even before accessing L1, right? So even before creating a request for the cache. How do I do that? I'm going to use this idea of virtually indexed, physically tagged. So before doing that, the first question is, can I access L1 using virtual address? Because if I do that, I don't even need translation. And the answer to that is no. Why? Why can I not just access L1 using virtual addresses?
There are going to be multiple programs that have that same virtual address.
Yeah, because I told you that programs had no idea about the existence of other programs in the system. So they think that their addresses start from 00. So there might be like an array that starts at address 100. There might be another program that also there is another array that happens to be at that same address. And since I'm running these two programs in parallel, they can be both thinking that they're accessing address 100, but in fact, they're addressing completely different things, right? So this is the problem we call aliasing, that programs happens to map into the same address. The reason for it is that our computers are not designed to know about each other's program, because that's a huge security issue, actually. You don't want to tell the other programs that what are the addresses of the other program. So I cannot directly use virtual address in any case or shape or form. But here's what we can do instead, is that if somehow I can search TLB and L1 in parallel, then again, I'm hiding the latency of the TLB. Because if my L1 anyways is slower than TLB, then I'm hiding the latency of TLB. How do I do that? Remember I told you that page offset is the part that I don't need translation for? So here's what I'm going to do is that my address has two parts, right? It has the VPN and it has the page offset. If I use my page offset to access L1, then I don't need translation. Okay, I can directly use page offset, access L1. I bring the data, and then I can look for VPN in the TLB and then bring the PPN. Then I'm going to check whether this address that I'm accessing, is it my program? Or is it some other program that happens to have the same page offset? So this way I can distinguish between the two. That is this address 100 of my program, or is it the address 100 of the other program? Because my PPN will be different than their PPM. So I'm going to compare the tags. Hopefully it will be mine. So basically it means that essentially all I'm doing here is that I'm searching TLB and L1 cache in parallel. So now my hit time essentially goes back to the hit time of L1, because L1 is basically this path. I'm still doing the same path. So this is why it's called virtually indexed, physically tagged. So as you can see, the indexing from the cache is virtual. So I'm using virtual address to index this cache. But the tag that I'm checking is actually a physical tag. Okay. So it's usually we call it VIPT, virtually indexed, physically tagged. Okay. So L1 cache, and then again, what is the hit time? It's a max of this and this. Typically, this is much smaller than this. So this is much slower. That's why it's going to be L1 again. Okay. What is the limitation? Is that the size of this guy should fit into this. And then there's actually a formula for it, is that the page size times the associativity of this cache should be smaller than the cache size. You don't need to worry about that, but just generally know that I cannot have arbitrary big size of L1 because the indexes within this cache should fit into this addresses. Typically, page size is fixed, is usually two kilobytes. So we don't go beyond like 4 kilobytes, so we don't go beyond 12 bits. So that's why the number of indexes I can have is at most 12 bits. Okay. All right, so going back to our boom, our I cache is virtually index physically tagged, and now you understand what that means. All right, so here's this just to wrap up. Here's the fetch. Remember I told you that we are looking at boom version 3. Those are the other ones that older versions. But essentially what we do is that we have 4 cycles of fetch. Okay. And within those 4 cycles, we do lots of things. We look at the BTB and take and other things. But at this point, we're going to put things into a queue, and then we're going to feed it to the rest of our design, including the decoder and renaming. Okay. All right. So that's all we have for. So there's going to be branch prediction and so on. That's all we have for now for fetching. Next time, we're going to talk about decoding and renaming. Okay.